So let's start today's seminar. It is a pleasure to announce the visit of Fernando Comerón here at the IC. His visit will be very short. He will be here today only. He is just on his way to La Palma for a meeting related to GTC and the ELT and the ING agreement. Fernando is currently the chief of the division on the data management and production of ISO, but he is combining actually his time on management duties and science. Unfortunately, today he is talking about science in this presentation. So thank you very much, Fernando.
Well, thank you very much, and thank you very much for this kind invitation to stop by the AAC and to visit you. It's always a pleasure to be here. It's especially a pleasure when you are coming from a place like Garching in the winter, where the difference in temperature is something like 20 degrees, and here you can see the sun and things that we don't have there. So I was trying to give a somewhat provoking title to my presentation, Young Stars in Lupus, Not What Expected and Not What Expected. What I mean by this will become clear towards the end of my presentation. But what I would like to start with is by motivating why looking at lupus is interesting or exciting. So why lupus? The lupus clouds are one of the nearest star-forming regions, low-mass star-forming regions in the solar neighborhood. It's a place where we can access lots of stars, lots of phenomena displayed by young, low-mass stars that we can study in detail, and we have plenty of those in the lupus clouds. In fact, some of the most some of the richest T associations of T Tauri stars in the solar neighborhood are located in the lupus clouds. They are about between 150 or 200 parsecs. Probably they are located both at 150 and 200 parsecs in the sense that it is a complex of clouds which probably span a range of distances along the line of sight. Another interesting aspect is that the lupus clouds that lie here in the middle of this plot, here in the middle, are sandwiched between two OB associations or two clusterings of OB stars belonging to the large Scorpius Centaurus Lupus OB association. So these black dots here are massive stars. This massive here. This, oops. Apologies for that. So these black dots here are OB stars, which in principle can have some effect on the star formation in lupus, and also in this neighboring region, which is also a well-known star-forming region, Rho Fucus, whose dynamics and origin and star-forming history may have had something to do with the presence of these massive stars. Lupus clouds sample a range of star-forming environments. It is a complex of several clouds. It's different from Rho Fuci in that respect, in that star formation is concentrated in several places, which are only loosely connected among themselves. And as I said, they contain a lot of examples of the phenomena displayed by low-mass star formation, like jets, pre-stellar cores, a range of ages in the objects that they contain, signatures of circumstellar disks that we can study in some detail and we can resolve physically because of the short distance, signatures of high accretion on top of objects that are being formed. So everything that one can be interested in the terrain of low-mass star formation is represented there. The topic I'm going to talk about, or the observational material that motivates the work that I'm going to present, has to do with a survey that we carried out using the 2.2 meter telescope on La Silla with a wide field imager of half a degree by half a degree field of view, which was kind of a byproduct, at least it was conceived initially as a byproduct of a legacy survey to be carried out with Spitzer, which is now fortunately completed. Survey of star-forming regions, composing the legacy program from star-forming cores to planet-forming disks, which is led by Neil Evans at the University of Texas, and has also an important European component, which is led by Wine van Dishoek, who is now sharing her time between Leiden and Garching. So the idea of the survey was initially to provide ground-based imaging and photometry for sources to be detected by Spitzer, so that the spectral energy distribution could be extended into the visible wavelengths, and specifically in the range where the emission is dominated by the photospheres of the objects, rather than by the disks, which is preferentially detected by Spitzer. So for that purposes, we carried out, we planned observations to cover the 3 clouds that were targeted by Spitzer, in particular by the MIPS instrument, which was the one having the broader coverage. Also, the observations were carried out both with MIPS at long wavelengths and by IRAC in the shortest infrared wavelength range. As you can see here, even if we call this a survey, and a survey of several star-forming clouds, the area covered is rather small. Here you have 2 maps at roughly the same resolution, an extinction map of the Lupus clouds, including all the Lupus clouds and even the low extinction regions, Lupus 1, 2, 3, 4, 5, and 6. And what you can see is that the regions most interesting regions from the star formation point of view cover a very small area, which you can see here, Lupus 1, Lupus 3, and Lupus 4. Therefore, what we are sampling is only a selection of regions, a selected area, which by far doesn't cover the whole of star formation in Lupus, or the potential star-forming sites in Lupus. This is still, even after our survey, largely an explored region, and one in which, for sure, there will be lots of things to discover in the coming years as future surveys probe more and more the clouds and their associated population. Here you have a picture of the 2.2-meter telescope on La Silla with the wide field imager instrument attached at the Cassegrain focus. The observations that we carried out were in the red to very near infrared, between 0.6 and 0.96 microns, RI-Z band. The Z band here is not the GAN Z band that you may be used to from Sloan, for example. It is Z Wi-Fi band, so named because of the filter in that instrument, which is actually located at 0.965 microns. Observations were carried out in service mode during 2 observing seasons, actually, in 2002 and 2003. I should admit that I am a bit embarrassed to present only now the result of observations that were carried out already 6, 7 years ago. But, you know, lots of things can happen in the meantime. They covered over 6 square degrees, in adding together the area sample in the 3 clouds, in fact, almost 7 degrees, with rather faint magnitude limits, up to 20-something, 3 sigma detection, with a limit also in saturation, which limits our ability to detect the most massive or the most luminous objects in the clouds, which have been mostly covered by previous surveys anyway. So, in principle, these observations were designed, as I said, to complement the Spitzer observations. But if you have observations of so many sources, hundreds of thousands, of, in fact, somewhat over 1 million sources observed in RIZ, and you can combine that not only with the Spitzer, but also with other surveys like TUMAS All-Sky Survey, you can get for a lot of sources, in fact, over 150,000 considering all the sources covered in our survey, spectral energy distributions that go from 0.6 from the R band all the way up to 2.2 microns. So that covers a lot of spectral energy distribution, and in particular it covers the most interesting part of the spectral energy distribution for low mass objects, for cool stars and for massive brown dwarfs. So that developed by itself in a natural way into a self-standing project. And in fact, the Spitzer observations turn out to be complementary of this project rather than the other way around. Also, the observations that I'm presenting here were also taken into consideration for several studies carried out with a focus on the Spitzer detections. So I'm going to talk mostly about the observations in the visible and near infrared rather than on the Spitzer observations themselves. Also, they will appear providing important complementary information towards the end. This is the questions that we try to address. When we study star-forming regions, we normally use a number of tracers of activity, of youth, in order to identify the census of the population. We use activity, we use the signature of circumstellar material, we use emission due to accretion or to outflows. And we want to use these censuses in order to study global properties, among other things, of course. The objects are interesting by themselves, but their collective properties are also quite relevant. Things that we try to address with these kind of surveys have to do with the study of the initial mass function, so a statistical property, global property of the star-forming region, the lifetime of circumstellar disks, the history of star formation, and plenty of other properties that have to do with the global stellar population in general. At the time of doing that, we have to be careful that effects of completeness are properly taken into account, and that if we are using the census to derive the global properties of the star-forming region, we take care properly of the objects that we don't detect by using these traces of Youth. So if the population is incomplete, if we suspect that there are incompleteness factors in the population, we want to know how incomplete it is, how this incompleteness depends on the mass, how it depends on the age. How can we identify the missing members, if at all possible? And a way to do that is to use not the traces of Youth by themselves, but to use the photospheric spectral energy distribution of the objects under study, specifically disregarding the signatures of Youth. That's something that comes only later, that we can use in order to assess how complete we have been when using the signatures of Youth. Using the red to near-infrared bands that I was mentioning at the beginning allows us to do this job pretty well for the kind of objects that we are interested in, for low-mass objects in a star-forming region. That's due to the fact that from the Earth to K band, so in the area that is represented here by these red dots, the sampling of the spectral energy distribution is quite good. In fact, what we are sampling here, as you can see right away in this figure, is the peak of emission of the photospheric spectral energy distribution, and a number of spectral features that happen mostly at red wavelength, where there are molecular bands, molecular features that are strongly dependent on the temperature. So by having a sampling of the spectral energy distribution in this spectral range, we can constrain very well the temperature, and in addition, we can disentangle very well the effects of extinction from the effects of temperature. So we can tell very well what part of the colors can be attributed to reddening, what part of the colors can be attributed to the intrinsic colors of the object. And in this way, putting things together, putting our survey together with 2MASS and applying fits to the spectral energy distribution that we obtain, we can estimate temperatures for over 150,000 stars, which is quite a respectable number. And these fits turn out to be especially reliable in the cool end of the spectral energy distribution. So far for the temperatures. Of course, cool objects exist in star-forming regions, but also out of star-forming regions. We have red giants, we have AGB stars, we have main sequence K and M stars, which have temperatures in the same range. And in addition, the effects of gravity that distinguish these objects are relatively mild in the colors. So we can get a good fit to the spectral energy distribution of an object in this range of temperatures, regardless of whether it is a young stellar object, if it is a main sequence star, or if it is a red giant. We need something else, and that else is given, in the case that I'm going to describe, by the luminosity. And what I'm going to show in the next minutes is that there is a simple way to characterize the population of a star-forming region like Lupus, using only the broadband colors and the fits to the temperature, and an estimate of the temperature of the luminosity, by doing the following. Let's consider the formula that you have here at the top, which is very similar to a formula that we are all very familiar with. This is the relationship between the apparent magnitude at a given wavelength, here, the small m, which is related to, typically, the absolute magnitude, the distance modulus, and the extinction at that wavelength. What you can see here at the top is very similar to that, only that I have decomposed it in a slightly different way. What we have here as capital M with a star is the absolute magnitude that the fiducial star with a radius of 1 solar radius would have at that given temperature. That's something that the synthetic spectral modeling can give us. In fact, the models published by the group of Allard, Hauschild, and Baraf give us, as the output of the models, this quantity. So a quantity that depends on the temperature and the surface gravity, but not on the radius. Then the part that depends on the radius, I offload here to this expression here, which contains the distance divided by the radius, which in general will be a function of the temperature and the age of the object. There is this factor of 5 for historical reasons, the way that magnitudes are described. And there is the dependency of on the extinction that I characterize, like this, that I characterize as the ratio of extinctions at a given wavelength over the visual extinction multiplied by the extinction, so that in this way we obtain an expression that depends on a constant factor, because this is given by the extinction law, multiplied by the extinction at visual wavelength, so something that depends only on wavelength. So in this way, the apparent magnitude of an object at a given wavelength can be expressed as the absolute magnitude of this fiducial start of one solar radius of radius, plus this parameter S, which depends on the distance and the radius of the object, doesn't depend on the wavelength, and the extinction. This is true for any star for which we fit the spectral energy distribution, regardless of whether it is a field star, a giant, or a member of the star-forming region. The distinction comes at the time of interpreting what this parameter S means. In principle, S is related to the distance modulus and to the age via the radius of an evolving object, so that for main sequence and red giant branch stars, we can derive it, or we can interpret it, taking into account that there is a relationship between radius and temperature. This is a loose relationship for red giant branch stars, which span a range of radii at a given temperature, but it is already good enough for our purposes. So in this case, for objects for which we don't know what the distance is, but we know that they follow a radius-temperature relationship, the parameter S is directly related to the distance at a given temperature that we fit from the spectral energy distribution fit. When we are considering, however, members of the star-forming region, for a given temperature, the radius normally depends on the age, which is unknown. But we can assume that all the objects are approximately at the same distance, at the distance of the star-forming region. Therefore, this parameter D, the distance to the star-forming region, is common and known by other means. And then the parameter S directly relates to the radius, and through the radius to the luminosity and to the age, using appropriate evolutionary tracks. Therefore, if we solve this system of equations for which we have one for each of the bands that we are considering, typically we'll have 6 equations of this kind with 3 parameters that are unknown, the temperature, the parameter S, and the extinction. We can solve for S and extinction for a range of temperatures and identify the best fitting temperature as the one that provides the least residuals to the observed magnitudes. So it's as simple as that. Does it work? Well, our numerical experiments show that the temperature in this way can be determined, and we can see large differences in the residuals if we change the temperature by plus minus 200 degrees. That we can check not only from the numerical experiments, from the quality of the fits, but also by comparing the results that we obtain to the results, to the spectra, the spectral types determined for the already known members of the star-forming region. There are plenty of members of Lupus that have been classified over the last decades, for which reliable spectral types are available, and therefore through spectral type versus temperature calibrations, for which we can get the temperature from the spectral typing. And what we get is quite encouraging. Here you have different data points that correspond to spectral types coming from different studies, from the literature. The dotted line and the solid line correspond to spectral type versus temperature calibrations carried out by other authors. And we see that things generally fit. So the objects for which we determine the temperature, this is in the vertical axis, our temperature determination, have spectral types known spectral types that correspond to the temperature that we infer. So the method works within the accuracy that we expect from the quality of our fits, and that gives us confidence that we can extend our fits, we can interpret our fits, or we can rely the temperature that we obtain from our fits for all the other members, or for all the other members of the cloud that we detect, and for all the stars that we detect in the surveyed area in general. There are a few discordant points for which we normally can find an explanation in terms of variability, or in terms of a strong circumstellar excess, or in terms of strong accretion lines which raise the flux in the R band predominantly. But these are a few, and they are known for the known population of lupus. So for about 70% of the members of lupus, so for a population that is likely to display these perturbing factors on the spectral energy distribution, we still find a good fit. So that's quite encouraging. This is a previous slide, so we have seen that already. This is how things look in a real temperature versus S diagram. This is a result of our fits, the best fitting temperature that we obtain, the S parameter. Here you have the red dashed lines, which correspond to two representative isochrones at the distance of the lupus clouds, at the distance of 200 parsecs in this case. We would expect that most of the members of the population comprised between these ages will fall between these two lines. You can see also the range of masses that these temperatures normally sample. And what you can see here is that most of the objects that we detect in this range of temperatures, regardless of any consideration about membership, fall below the 20 million years isochron, fall here in the lower part of the temperature S diagram. So this is the foreground population, most of the population. Most of the objects that we detect in this temperature range are irrelevant for us. They are foreground, they are old main sequence of all the stars, so not the population that we are looking for. You can see that this population has also a tail at low values of S, so this corresponds to luminous objects, many of which fall between these two bands, and some of them fall well off these bands. The objects that you can see here in the upper right corner are most likely background giants, which we expect to find in this part of the diagram. But what we see in between this concentration of points in the lower left and the few points in the upper right are the objects of interest for us, especially at low temperatures. This is where we expect to find the members of the lupus clouds. So let's try to do it, and let's see what we get. This is another way to see the same, which reveals several interesting features. It's difficult to see at this magnification, but this is a comparison in different temperature ranges between models and reality, and the number of objects that we detect, taking into account everything, including members, including background contamination, including foreground contamination, in the direction of the Lupus 1 cloud, here on the left, the left bar, in the Lupus 3 cloud, here in the middle, and in Lupus 4. So let's pay attention for a moment to these two lines, these lines that you can see here and here. The line on the left represents the foreground population. This is something that we can model from the local initial mass function, which will tell us how many objects we can find within a given range of temperatures at given values of this S parameter, coming from a normal initial mass function represented by stars seen at different distances. So this is the foreground contamination. We see that when we go to high values of S, just for reference, this is S equal 10, this is 8, this is 6, so that it cannot be read here. We expect the foreground population to dominate. Most of the objects at these values of S are foreground. And what we find in our histograms is that, indeed, the population that we do detect dominates at these ranges of S. When we move to low values of S, to the brightest objects, we expect the background population to take over. Very distant red giant branch stars to be the main contaminants at these ranges of S. But these objects are rare, they are very distant, and if we have to make them faint enough so that they become a substantial source of contamination of the population belonging to the Lupus clouds, we have to place them very, very far away. So far away that they go out of the galaxy. They go to regions of very low star density. Therefore, we expect to find very few contaminants, background contaminants, at relatively faint magnitudes. Fortunately, we live in a region of the galaxy in which, if we consider stellar populations between a distance of 100 and 300 parsecs from us, the populations of a few million years old young stellar objects belonging to them are going to fill exactly the gap between the foreground population and the background population. So if you see, for example, Lupus 1, to start with, you see that our histogram shows, indeed, the background population shows almost nothing in the, foreground population here, almost nothing in the background population, because these objects are relatively bright and therefore saturated in our images. So expect a typical red giant branch star to be saturated. So we don't detect it. We cannot fit the spectral energy distribution. But we have a secondary peak here in Lupus 1, clearly seen here in this part of the histogram, here, also at cooler temperatures, here and here. We see it even more prominently in Lupus 3. Look here, a broad peak, which subsists as we go to lower and lower temperatures, and it is almost absent in Lupus 4. So this is a signature of the population associated with the clouds. We have, in our histograms, something that we cannot explain purely in terms of a foreground and a background population, something that must be intrinsic to the clouds that is not taken into account in our modeling of the foreground and background. I should say that we are fortunate that we can do that with the Lupus clouds, because they lie at the right distance. If we go to a more distant region, like, for example, Orion, or farther away, this peak produced by young stars moves towards fainter magnitudes, toward higher values of S, and therefore it gets hidden by the foreground population. If we have a population that actually doesn't exist, but could happen within 20, 50 parsecs from the sun, let's say, their members would be so bright that they would mix with the background population of red giants. Therefore, it works only between approximately 100 and 300 parsecs. But we are fortunate because not only Lupus, but also Rho Ophiuchi and Ercoran Australis, the chameleon clouds, the Taurus clouds, fall in that region. So we can apply this method to any of these star-forming regions, and it should work. It certainly does work for Lupus. So this is what we find in terms of the properties of the different star-forming regions, of the different star-forming regions that we have studied in Lupus. In Lupus 1, you can see that that most of the objects that we detect that are represented here by the empty circles actually dominate the population. What we are comparing here in this temperature versus S diagram, which you can interpret to a first approximation as a temperature luminosity diagram, in which we can plot also isochrons and evolutionary tracks. These are objects that are selected from our sample exactly in the same way. At this stage, we don't make any distinction between known members or non-known members. These are objects for which we can fit a temperature and we can derive the value of S. And then we look which ones of those were already known from previous surveys. The ones that were known from previous surveys are the black triangles. The ones that we find as new are the white circles. The dotted lines here represent a restriction that we have to impose on our identification of members due to the existence of foreground and background population. In principle, we could look for members that, for some reason, happen to have a lower luminosity that puts them in the domain of the main sequence foreground population, for example, due to the presence of obscuring disks seen almost at John. We know that decreases the apparent luminosity of an object while roughly preserving the colors in the visible and the infrared. We haven't done that in order precisely to avoid the background population. If we remove this limit, this dotted line, and we plot all the objects that we find in this range of temperatures and S, here at the bottom, we would have a lot of contamination by foreground members. So we would be washing out completely the population that we are interested in. So we detect many members of Lupus 1, and in addition, most of the ones that we detect were not previously known. So the next thing to do is to look where these objects are located. So here you have a map coming from our wide field images of the Lupus 1 cloud. You can see that there is a reach of nebulosity, of dark nebulosity, that runs from the top right to the bottom left. Here it is, roughly this. You can see some blank areas in this negative image. And you can see that even if most of the known population of Lupus 1 concentrates towards these clouds, it is deeply embedded objects for which we don't have air and dye photometry, so we don't fit a spectral energy distribution to it. Most of the objects for which we do detect for which we do fit the spectral energy distribution are located off these clouds. There is a loose concentration towards the center of this image, but very little on top of the clouds. Very little here, and on the secondary concentration, which is located roughly down here. So we can fit also spectral energy distributions for three objects that happen to follow to fall on the dark clouds, this one here, and these two here and here, but the rest falls off the clouds. In addition, if we look at the Spitzer results for these objects, we find that only one of them, one of these new candidates that are represented here by red squares, is detected with excess emission at 24 microns. So only one of them shows signatures of warm circumstellar dust. The other ones don't seem to have circumstellar dust, at least at the temperature warm enough to produce excess emission in the Spitzer bands, ranging from approximately 4 microns up to 70 microns. In Lupus 3, the effects are even more dramatic. Lupus 3 is richer in every sense. So we detect more members, and we detect also, many of the objects for which we fit the spectral energy distributions are already known members. Here we have also limits that we have to set in order to avoid background contamination. So this is the lower dotted line here. But also in this case, since Lupus 3 is at lower galactic latitude, we have to set a limit, a bright limit to that we could skip in the case of Lupus 3 to avoid contamination. In fact, these three objects that appear here are most likely background giants, and the brightness fits with the fact that they could be red giants. So several interesting things to notice here in this more populated diagram than for Lupus 1. First is that our new objects are mixed in terms of location, in terms of location in the temperature S diagram with the already known objects. In other words, if we compare the position with respect to the isochrons of these two populations, known versus unknown, there is no significant difference between them. So our new members, or new candidate members, span the same range of distance of ages as the already known objects. Second thing that is interesting to note is that we have kind of plenty of wrong buttons. Let's see. We have an empty area here in the wrong button again. Sorry. This is the third time I'm going to try, and this time I will get it right. Yeah? Here it is. So we have an empty area above this kind of envelope. So nothing here except for the contaminants, which are far removed from the rest. And this is likely to be the birth line of young stellar objects at the distance of Lupus 3. So objects with ages of about a few 100 million years. For reference, the first solid line here is the 1 million year isochron. This is 5 million years, the second line. This is 10 million years, 50 million years, and the main sequence. The division between brown dwarfs and very low mass stars lies here. These are objects in the border, this line here. This is 0.05 solar masses, so massive brown dwarfs, and these are 0.02, so objects with 20 Jupiter masses. So we see here the birth line, and we see a mixture of ages. And again, when we compare this to what is known from Spitzer for these objects, we find that very few of them among the new candidate members have infrared excesses. The distribution in the sky is, again, somewhat surprising. If we consider the objects that were already known, these are the blue triangles here, they concentrate, as was already known, towards the main dark cloud composing Lupus 3, this region here. So you see that most of the blue triangles are on or near this area, with a few stragglers away. But most of the objects that we detect as new candidate members are located off the cloud. So clearly the radial distribution with respect to the cloud, even if in the case of the new candidate members there is a certain loose concentration towards the cloud, most of them are clearly located outside it. This is not a bias of the extinction, the fact that the new members and the old members the new members, since they have been detected by other means, and many of them by their emission in the Spitzer bands, can be located when they are more embedded in the clouds. This is not the case because this is an unbiased comparison between the two populations. The blue triangles are not all the known objects in Lupus 3. They are the known objects in Lupus 3 that we detect with our spectral energy distribution fitting method. So, in principle, these are objects for which a priori we don't have any information on whether or not they are members. Only when we look at catalogs of known members to see if they were known or not, we find that the known members are more concentrated towards the clouds. So the spatial distribution of these two populations, again, seems to be different as we had found for the case of Lupus 1. Finally, Lupus 4. In Lupus 4, we explored an area which was about 2.5 times smaller than in the other two clouds because it's more concentrated in space. The number of objects that were known in Lupus 4 before our study was about 16, which is very similar to the number of objects that were previously known in Lupus 1. But contrarily to what happens in Lupus 1, we detect very few new objects, new candidate members in Lupus 4. Very few. Only one of them is detected by Spitzer, but without infrared excess, so it looks like a normal photosphere. Again, no traces of a circumstellar envelope. And clearly, the surface density of new members is well below that of Lupus 1 and 3. Remember, in the other maps, we had plenty of red squares concentrated towards the cloud. Here, we don't have plenty of red squares. We have only a few of them, and clearly, they are not concentrated towards the dark cloud that falls here towards the middle of the picture. So no trace of concentration toward the cloud or around Lupus 4. So we can summarize the results thus far by saying that the method works when we compare to the known population, that we find new populations of candidate members in Lupus 1 and 3, but this is nearly absent in Lupus 4. The new populations are especially concentrated in Lupus 1 and 3, but not as closely concentrated towards the dark clouds as they are in Lupus 1 and 3. We don't find a significant age difference between the known and candidate new members. This is not only from applying isochrons to fit the distribution of, to fit the spectral energy distribution of objects. These are relative comparisons, so if the isochrons that we are considering to fit the ages don't work or are biased, they are biased the same way for the candidate new members and for the non-members. And finally, the new population doesn't have high diffraction. In fact, disks, signatures of circumstellar disks, are very rare among this population. Or, to be more strict, more careful, there are no traces for inner disks, for warm disks. Taking into account that the Spitzer wavelength coverage goes all the way up to 24 or 70 microns, depending on the brightness of the object, we cannot say anything about the possible existence of extended circumstellar envelopes with large inner holes, which would reveal themselves only at several hundred microns or even in the submillimeter, in the millimeter, submillimeter regime. So what we can state about the absence of disks corresponds only to the few inner AUs with respect to the central object. So typically between 1 and 5 AUs, which incidentally is the most interesting region when one wants to consider the implications that this has on the possible formation of planets around these objects. Well, there is a caveat that I haven't mentioned before, which is when we have modeled the foreground and the background population, we haven't taken into account a component that was discovered about 1 decade ago, thanks to the Rose et al. All-Sky survey, which is associated with the Gould Belt. The Gould Belt is the large stellar system that contains most of the star-forming region in the last 30 to 60 million years around the Sun, extending up to a distance of about 600 parsecs or 300 parsecs, depending on which direction of the sky you look. It is tilted with respect to the galactic disk. So in some directions, you can see the Gould Belt practically uncontaminated by the foreground and background population of the galaxy. And since the Gould Belt is composed of members that have ages of several tens of million years, one could expect that this population is youngish, but may not have already the disk signatures, which, due to the disk dissipation or to the process of inner disk clearings, goes away after a few million years, not after a few tens millions of years. The Gould Belt is extended in the radial direction. So if we look in the direction of Lupus, which is located in the Gould Belt, we expect to see some foreground population composed of objects that are more evolved than the members of the Lupus clouds, but since they are closer to us, even if they are intrinsically less luminous, they appear with similar apparent magnitudes, just because the range of distances happens to be the right one to mimic the luminosities of the apparent luminosities of the cloud members. So this population is a potential contaminant, and it is therefore a possible contribution and a possible explanation to the new members that we find that have not been selected by other methods based on the signatures of Youth, simply because the signatures of Youth for these members, for these objects of the Gould Belt, are long gone. We believe, however, this is not the case, and we have several reasons which I consider to be quite compelling to argue that the new population doesn't belong to the Gould Belt. Let me make just an inset here. When we first identified this population, I really did want it to belong to the Gould Belt, if only because of a sentimental attachment. The Gould Belt was the topic of my PhD thesis, and with the years you develop a kind of attachment to this topic. So, despite the fact that I love the Gould Belt, I believe that these objects don't belong to it because, as you can see in the previous slide, the population belonging to the Gould Belt here in the left panel is spatially distributed over angular scales that exceed several tens of degrees, which is much smaller than the size of the clouds that we observe. Since we observe spatially concentrated populations in Lupus 1 and Lupus 3, the typical angular scale for the distribution associated to these clouds is much smaller than the population associated with the Gould Belt. Therefore, we wouldn't expect to see the new members concentrated as we see them. In addition, on the sky, Lupus 3 and Lupus 4 are very close together, a few degrees of each other. If this was a foreground population belonging to the Gould Belt, we would expect the surface density of objects to be very similar to in the direction of Lupus 3 as in Lupus 4. However, in Lupus 3 we find plenty of objects, and in Lupus 4 we hardly find any. So there is clearly the population that we detect in the direction of Lupus 3 is clearly associated with Lupus 3 and not with a much more widely distributed population like the Gould Belt 1. In addition, there is this birth line that we observe in Lupus 3, or something that we interpret as the birth line. This depopulation of objects that you may remember in the upper right part of the temperature versus F versus S diagram, that if we had a population belonging to the Gould Belt distributed at different distances, there would be no reason for it. There would be no reason for this cutoff. We would have to see that population of the diagram more or less similarly populated as the regions where we do find the new candidate members. I'm on the wrong slide, actually. Here it is. So, angular scale, concentration of objects towards Lupus 1, Lupus 3, not in Lupus 4, which is close to Lupus 3, and radial thickness of the Gould Belt, which would wash out this apparent birth line that we detect in Lupus 3. So that doesn't mean that none of the objects that we detect can belong to the Gould Belt. Possibly some of them are. In fact, it is likely that all of the objects that we detect in the direction of Lupus 4 belong to the Gould Belt. We would expect a few in that direction. But certainly they are not the dominant population in Lupus 1 or in Lupus 3. So these are the facts. This is what we detect. This is how we interpret it. And the rest of what I'm going to say, please take it as speculation about what the origin of that new population could be based on what we know about it, based on the observational facts, on the distribution of ages, similar to the known members, and on the absence of disks. So first possibility, the one that comes immediately to mind, is that the new population could be composed by older members that are not as old as the ones in the Gould Belt, but that perhaps represent early stages of a star formation in Lupus 1 and Lupus 3. Let's say the population that is 10 million years old. This population would have had time to drift away from the star-forming clouds, so we would see it as a spatially distributed population, as we do. The ages would be older, so they would have had more time to disperse their circumstellar disks. So that's consistent with the Spitzer observations. But the fact is, as I have pointed out several times, that there is no evidence for any significant age difference between the population of known members and the new population of candidate members. Of course, the age determination is subjected to observational uncertainties and to interpretations depending on the isochrones that we use. But differentially, we don't see any difference. And that difference should be there if indeed these objects belong to populations with different ages. So we believe that this is not the case. Of course, once we have detailed spectral classifications for these members, if we can determine their luminosities better, if we can place them with more confidence in the temperature luminosity diagram, we may find that there is some difference. But at the moment, from the evidence that we have at hand, there is no hint that such a difference does exist. Second possibility is that the two populations are coeval, as we infer from our observations, but that the distributed population, the new candidate population, is composed by objects that have been expelled from the clouds by tidal interaction, by close encounters with the cloud members, with other cloud members, and expelled out of the clouds, and in the process disturbing and eventually losing their circumstellar disks. So ejection from the main clouds. We believe that this is not the case either, because if this mechanism is at work there, it should be extremely efficient. Because in the case of Lupus 1, and it's also close to the case in Lupus 3, most of the objects are actually belonging to this population. Most of the members are belonging to this spatially distributed population. So most of them should have experienced this disk stripping encounters followed by ejection in order to account for the numbers that we observe. That seems hard to believe. It's quite implausible. Again, it doesn't mean that we may find some specific examples of objects that have been expelled through these mechanisms. But we don't expect it to be the general case. Perhaps more interesting is the possibility that the environment in which the Lupus clouds are located plays a role in this. Remember, I said at the beginning, Lupus clouds are sandwiched between two OB associations that contain massive stars, which do a lot of damage to their surroundings within a few parsecs around them. So take into consideration that this distributed population is away from the main clouds, therefore they are somehow unshielded against the radiation from these these nearby OB stars. This is not new. It's something that in fact is well documented and well observed in the trapezium cluster, in which we can see the disks thanks to the impressive Hubble images of circumstellar disk around low mass stars in the trapezium cluster, the famous proplets. This has been modeled. Indeed, we know that the ultraviolet radiation by a nearby star has an eroding effect on circumstellar disks. But the problem is that, on the average, the stars in Scorpio Centaurus lie well too far from the Lupus clouds. It's much farther away than the surroundings of the trapezium stars in which we observe these disruptive effects. So we should invoke either more massive stars existing in the past and more closely embedded in the Lupus clouds, or simply a different effect. So on the paper, massive stars could play a role. In practice, the distances involved, for what we know of the current OB population in the Scorpio Centaurus associations, tells us or hints at this mechanism to be highly inefficient in disrupting, in dispersing the circumstellar disks in Lupus. A fourth possibility, which is somehow related to this one, it still has to do with the environment, and in particular with the massive stars in the environment of the Lupus clouds, is that in situ formation of low mass stars in Lupus may have been triggered by distant supernovae. This is a mechanism that is appealing for the explanation of many features observed in star-forming regions. It is a mechanism that was explored for our own solar system as the triggering mechanism of the formation of the sun and planets, based on isotopical peculiarities in meteorites that are difficult to explain by the quiescent collapse of an isolated cloud, which suggests that there was an early injection of radioactives in the early presolar nebula. But what matters here is that even if close to the supernovae, the shock fronts that the ejector drive ahead of them are highly disruptive, and they would tend to destroy rather than to trigger star formation in pre-existing clouds. When these shock fronts move away and pile up circumstellar material ahead of them and become slower and slower, they become much more friendly to star formation. And in fact, when you are several parsecs away from a supernova that has created a bubble of piled-up material around it, the net effect on a pre-existing cloud is to embed it suddenly in an environment of higher pressure, to squeeze it in this way, and to drive it above the stability threshold so that the cloud collapses. And it collapses in a way that is quite different from the typical collapse of an individual, of an isolated cloud, in that it is not an inside-out collapse, as we think that isolated collapse proceeds, but it's rather an outside-in, an externally driven collapse, which leads to some interesting quantitative differences. The one that is perhaps more relevant here is that the collapse is characterized by an early stage of very intense accretion, which heavily depletes the circumstellar envelope, leaving much less material for the formation of the circumstellar disk. And this may be why objects formed by this mechanism may be deficient in disks, at least after a few millions of years of evolution, because perhaps they didn't have them in the first place, or they had something that was much less massive than the disks that we observe around other stars that may have formed through more peaceful mechanisms. Even if this interpretation works for the Lupus clouds, at least in a very qualitative way, because you don't need any more nearby supernova. In fact, a nearby supernova, two nearby supernova would be pernicious for this triggering mechanism. We have plenty of massive star formation that has taken place over the last several millions of years in Scorpius Centaurus. So we have lots of progenitors of these slow shocks that may have run over the Lupus clouds over a span of several million years, which in fact may explain also the scattering ages that we find again among the new candidate members. One should stress, however, that quantitative simulations would be necessary to determine first if supernovae at, let's say, a distance of between 5 and 10 parsecs, which is a reasonable assumption for the OB stars with respect to the Lupus clouds, would produce shocks adequate to trigger the collapse of these pre-existing cloudlets. So the model needs to be worked out better in that respect. And in addition, we also would need to have more detailed simulations about the collapse of these clouds in order to indeed validate the underlying hypothesis that the outside-in collapse results in a population of disks with properties significantly different from the ones of better studied disks formed in other conditions. So this is just speculative, but at least we have several possibilities to choose from, some of which have a higher degree of likelihood than others, and different degrees of appeal than others. So finally, well, I wouldn't consider that this is a finished work. There are a lot of things that one can do. This is just a preliminary overview of what we have been able to do with broadband photometry over a wide area. Now we have a lot of candidate members that we can examine in more detail, and on which we can learn a lot of things that will help us to characterize them more rigorously than we have done so far, and to look into their details. First things to know is if these objects are indeed members of the Lupus star-forming region. For the ranges of masses of the objects that we detect, we would expect lithium to be a valid criterion to decide whether or not these objects are evolved or not, if some of them may be main sequence interlopers. We also would like to look for accretion signs. We know that there are objects that don't show circumstellar disk signatures in the Spitzer band, but still they have H-alpha, showing that there is some degree of accretion by the remnants of some circumstellar disk. So this could happen. We would like to exploit better the visible and very near infrared photometry that we have, the RIZ bands, by combining it with something that goes deeper in the infrared than the two mass catalog that we have used. And the upcoming VISTA telescope on Paranal would be an excellent candidate to do that, so that we can exploit not the 150,000 objects that we have observed, or that we have analyzed so far, but the 1,200,000 objects that we have, for which we have RIZ band photometry. This would allow us to go well into the brown dwarf domain, and to characterize the initial mass function of this population in a much more sound way. We would like to see also if these features are found in other star-forming regions. We have compared Lupus 1, 3, and 4, and we have found differences among them. We have found that there is a population in Lupus 1 and 3, there is no population in Lupus 4. What about the other ones for which this method is accessible? There is a work that has been carried out on Chameleon 2 by Loredana Spetzi, who is one of the collaborators in this project, and in which the characteristics found there are very similar to the ones of Lupus 4. So it seems that only a few selected clouds, Lupus 1, Lupus 3, perhaps others, do these extended populations. The maps that I have shown show only the cores or the regions closer to the dark nebulosity in these clouds. Is there something beyond that? This distributed population, how far does it reach? This has also important implications about their origins. We would like to know also if the absence of disks is a total absence of disk, something related to clearing of the space within a few astronomical units from the central object, or if it extends farther out. Herschel will be very important in answering this question. It will be sensitive to more distant and cooler dust, and will tell us if these are objects that lack inner disks or that lack disks or circumstellar envelopes of any kind. An interesting thing to do would be to validate one of the possibilities that I have mentioned about the possibility that OB stars are destroying, are eroding, and dispersing the disks of these objects by trying to detect disk of operation signatures, trying to detect disk outflows whose origin we can trace to the hard radiation of OB stars. There is a point that I didn't go through, but it's also quite puzzling in the population that we detect, that has to do with X-rays. We need X-ray observations over a large area to determine whether or not these objects are X-ray emitters. This is another signature of Youth, one that is longer lived than circumstellar disks or signatures of strong accretion, and one that should definitely be explored. Finally, we have been sensitive to the coolest stars for which our method works. When we move to hotter stars, interestingly, the background contamination washes out this valley in which we could detect the population of Lupus and makes it plainly indetectable. The contamination for solar-type stars, or objects that have G to early K-type spectra, is undetectable by our method. This is a population that is hidden in plain sight. We detect it, we know that if it is there, we are seeing it, but if it doesn't have any signatures of Youth, our method doesn't work for them. So we should be more clever and to try to find other ways of identifying it. An obvious way, and one that will be available in perhaps a decade from now, is astrometry. When we have astrometric trigonometric parallaxes towards these objects, we will be able to obtain full censuses of any star-forming region within this distance range, and we will not have to resort to these tricks that work for certain range of ages, certain range of temperatures, certain ranges of distances. And there are plenty of other things that one can do with this population to study it better, but perhaps the most striking conclusion of this work, and certainly for me the most unexpected one, is that most members of some star-forming regions, at all ranges of temperatures, certainly at the range of temperatures that we have probed with this study, may be hiding there in plain sight. So somehow stressing the fact that there is still a lot to learn about the composition of these star-forming regions, about their history of star formation, and about the processes that may have triggered star formation in them. All right, now we'll stop here. Thank you very much.
Fernando's agenda is very tight, so there is time for one or two questions. Comments?
A very nice talk. Just a question. Do these findings have any impact on the IMF of these regions?
That's something we haven't been able to explore because we have to limit the regions of the temperature versus S diagram in such a way that we probe different isochrons as we move in temperature and as we move in mass. So, in principle, it's possible to try to reconstruct the IMF from the data that we have, but we could do it only at the cost of introducing assumptions on the completeness, on the members that we are not seeing because of saturation effects or because of these cutoffs in S.
Bring it from the other way, actually, is there any difference in the IMF without considering the new populations between the IMF in Lupus 1 and 3 and Lupus 4?
We don't. In Lupus 4, it's very hard to tell because we don't have enough objects. In Lupus 1, in the range in which we can probe a significant, a relevant range of ages, we have too few objects. Most of the objects that we detect in Lupus 1 are actually at higher temperatures than the ones that we can identify in Lupus 3 because of the fortunate fact that Lupus 1 it is at higher galactic latitude, and therefore we don't have to be concerned as background contamination. The interesting comparison that we can do, and I believe that this is very relevant to your question, is we can compare the population of new members and known members in Lupus 3 itself, and see if the new candidate members, let's say the disk class population, has a difference in terms of mass distribution with respect to the population that has been detected by other means, a population that typically has disk or accretion or X-ray emission. And the answer is that, again, the same that we don't detect a difference in ages, we don't detect a difference in the distribution of masses for these objects. So the initial mass function for both populations seems to be the same, at least to the extent that we can determine with our observations. So whatever is the initial mass function, which we cannot tell, what we can tell is that the new and the old populations don't show differences in those terms.
Okay, Fernando will be here the rest of today. He has a meeting in less than an hour, but during the afternoon, early evening, he will be around. So if you want to talk to him, he will be here. Okay, so let's thank Fernando for his presentation.
Thank you. Gracias.
Resultados muy interesantes. Estoy de acuerdo contigo que os falta espectroscopía para completar, ¿no?, el análisis de la juventud. Pero, ¿tenéis pensado escribir algún artículo o tenéis ya un artículo enviado?
El artículo está en el segundo paso por el referí. Ajá. Y las noticias, el primer paso, fueron bastante buenas. El referí fue Bruno Merín, que naturalmente puso todo el énfasis en los datos de Spitzer.